Hey, Year 11, we're up to 9J, which is minimum spanning trees. Before we look at what a minimum spanning tree is, I'll try to find them. Let's have a look at what these words actually mean. So tree, that's something new for us. And it's a connected graph that contains no cycles or loops. So I'm going to get you to look at these couple of examples here. Now this one is a tree and this one isn't. Now this one is a tree because we can see all the vertices are connected by edges. There's no loops and there's no cycles either. So if there was a cycle, we might have to connect another edge. But another way you can kind of think about it, which I think is easier, is that a tree only has one face. So with this one, we can see we've got one face that's outside the whole thing. Whereas this one here, which is not a tree, we've got one face there, we've got a second face that's outside the whole thing, and our third face is in that little loop. So if you see you've got a loop there, or perhaps you've got a cycle sort of thing like that, that's no good. That means they're not trees. So this is not a tree, and this one is. Let's go back up to some definitions. So a spanning tree is a tree that connects all the vertices. So if we have a look at this graph that I've drawn just here, we can see that we've got a whole heap of vertices and a whole heap of edges, but it's definitely not a tree because we can see that there's cycles all over the place. So what I might do is try to come up with a tree. So let's just start here, go to there, I've already done that one. Then we might go to, go down here if we want to, and there, we could go there as well. Might connect that one too. Then we could go across here, there, and there. So hopefully if you focus on just the blues there, you'll be able to see that there's only that one outside face and all of the vertices are connected. Now that's not the only possible tree that we could have from that graph. I've got another identical one down here. I might just like randomly do another one. So again, we can start from the same spot. We can move over here. Then we might go like that, connect that one there. We could even use that one, then that one, and then finish off there. Do we see how these are both trees because we only have that one outside face? Remember, we're looking at the blue lines. But they're totally different. Okay, so there is often many possibilities for different trees. But let's look up here at this blue piece of writing here. The thing that we're mainly doing today is finding minimum spanning trees. So we had a couple of trees down here, but for a minimum spanning tree, we're basically trying to connect all the vertices using the edges that have the least weight. Now these ones here, they didn't have any weights, did they? So if perhaps this one had like numbers, so maybe 5, 2, 6, whatever, that would be a weighted graph. So we're going to be looking at weighted graphs and we're going to be finding the trees that add up to the least numbers. So let's just do this example here, which is pretty much the same graph as I drew before, but we've got a weighted version now. So there's a few ways to do this, but I think the most effective way is choosing your edge with the least weight to start with. So if you have a look around, we can see we've got an 8, we've got a 14, we've got a 9, we've got a 6, but the lowest is 1. Okay, so I'm going to use that one to start with. So that's connected H and G for me. What I might do now, and I've actually missed one, that's supposed to be 2. What I might do now is continue trying to connect them, but use the smallest numbers possible. So I can see there's a 2 here, so I'll use those ones to connect. And now from this one, I can see I've got a 10 to get over here, a 14 there, and a 4. They're bigger numbers. So what I might do is use that 4 to go over here. So I've connected a few now, which is awesome. All right, now I need to make sure I get to D. And I could go 14 or I could go 7. So I need to use the lower one. So I'll use the 7. So we'll connect to D. We need to connect to E though. So should we go from F to E and spend 10, or should we go from D to E and spend 9? Remember, we want the smaller numbers, so we'll use the 9 instead. Here we go. Now, we need to get a few different ways. So I want to get to I. I can get to I that way, or that way. 2 is the lowest, so I'll use that. but there's still a couple more that I need. I need A and B. So I could go 8 to get to there and then another 4, or I could go 8 and then another 4. It doesn't matter. They're going to be the same numbers. I might just go this way. We've got there and we've got there. So that would be our minimum spanning tree for this weighted graph here. Now if you add them all up, I think you'll get to 37. So I don't think you're going to find a spanning tree that it has a lower weight than that one there.